What I have here is a galvanometer, and a galvanometer is a microammeter. I can change the sensitivity of it using this dial on the side. So I might adjust that over the course of this demonstration. What I'd like to do first is just take a wire and a horseshoe magnet. What I'm going to do is I'm just going to pass the wire through the field, and I want you to observe the effect that has on the galvanometer needle. So you should have sort of seen a small deflection to the right. Let's move it back through. Now we get deflection the other way. Let's turn the sensitivity up a little bit. Do the same thing. Deflection, deflection. Now, there are a number of things which will affect the size of the current induced in this wire. First of all, you should be familiar with the fact that it's due to cutting of field lines or a change of flux linkage which causes an induced EMF. So the fact that if I hold the wire stationary in the field, nothing happens. Whereas if I move the wire through the field, I'm cutting lines of flux and therefore get an induced EMF. I'm not, in this video, going to go into the detail of how you calculate the direction of the induced EMF. I'm simply demonstrating the effects. So that's one way we can do it, by moving a conductor through a uniform field. Let's do something else. You'll be familiar with the fact that another way you can produce a field is by passing a current through a coil. So I'm going to use a second coil here, and I'm going to place it in close proximity to the lower coil. So I've got this coil connected to a galvanometer, microammeter, this coil connected to a power supply. Think about what's going to happen. When I put a current through this coil, it's going to create a field around itself. We're going to create an electromagnet. Is that going to cause anything to happen in this second coil? So have a think. You might want to pause the video and have a think. What I'm going to do is I'm going to switch the current on now in this coil. So I'm going to energize this coil, create a magnetic field. So we've got deflection to the left. I'm going to turn it, so now it's on. So now there's a current flowing through this. There's a magnetic field around it. But if you think about it, because the current is coming from a DC supply, it's constant, fixed direction, the field lines are going to be stationary. It's a static field. No field lines are being cut. There's no change of flux linkage through the second coil. If I turn it off, the current, the field goes from being strong to being zero. So that's a changing magnetic field. So what's important is that whenever there's a changing magnetic field, we're getting an EMF induced and hence a current induced in that bottom coil. I'll turn the sensitivity down even more so it stays, the needle stays on the scale. So you can see if I turn it on and off, I can effectively create an alternating current, which then creates or induces an alternating EMF across an induced AC current within the second coil. Next, this is a retort stand. It's made of iron. What I'm going to do is I'm going to place this inside the two coils. And we're going to see what effect that has on the induced current. So let's take it out and just watch what happens again. So you can see the deflection there reaches not far off, about here. So that's the peak to peak. Let me put the iron retort stand inside. Think about what's going to happen. What do you expect to happen? Pause the video, have a think. I'm going to do the same thing again with the iron retort stand inserted. can see the deflection has got larger. Because this is an iron core. Okay, it's thin, it's long, but it's acting as an iron core. It's magnetizing in response to the magnetic field created by this first coil and strengthening the field in the vicinity of the second coil. Hence, we're getting a larger effect. So that's a good example. What I've effectively made here is a transformer. It's a very odd looking one, but it's a transformer. What's amazing about this effect is before Faraday did this in the Royal Institution lecture hall, and that was 1831, let me just check my cheat sheet, 1831. No one had actually demonstrated that it was possible for a signal, effectively, to traverse space between two conductors. What we've got here is effectively the beginnings of wireless communication, because I'm flicking this on and off, yet getting a measurable effect in a coil which is separated and not in electrical contact with it. So if you think, first example of wireless communication, you'll see exactly how groundbreaking this demonstration that Faraday did was. It literally changed the world.